Okay, so I'm going to show you a more complex experiment now and how transformers work with use of an oscilloscope and a signal generator. Again, I'm using the Locktronics kit, which is available from Timstar, as is a similar oscilloscope and signal generator. So what you can see here is that I've put in place a very simple circuit. We have a signal generator providing a 50 Hz C waveform at 10 volts, a gap in the circuit here which is where I'm going to place a transformer, and then an output with a 1K resistor to provide a little load. I have an oscilloscope here, and this is a PC based oscilloscope to measure the input and the output. Channel A is measuring the input, whilst channel B will measure the output. So let's start with a really basic transformer here. So here I've got two 400 turn coils placed next to each other on a standard Locktronics carrier. The primary coil is energized by the 50 Hz signal to produce a corresponding magnetic field around the coil. As the secondary coil is placed next to the primary coil, it picks up a magnetic field and converts it into AC current, which flows through the resistor, producing a voltage that we measure on trace B. So if I put this simple transformer in place, you can see the waveforms on the scope. Okay. Notice that the secondary voltage is much smaller than the primary voltage, maybe 20 times smaller. You can see the scales on the left and right hand side of the oscilloscope reading. Currently I have them on auto scaling, but if I put each on 10 volts, you can get a better feel for just how much smaller the secondary voltage is. It's around 20 times smaller. So we have a reading on the primary of 2 volts and a reading on the secondary there of just above 0 volts. Now, from your theory, if we have a transformer with the same number of turns on the primary and secondary, you would expect the exact same voltage to come out. However, this assumes that the coupling between primary and secondary is perfect, and this isn't the case here. The problem is that energy does not travel well through air. However, energy travels much better through something such as iron or ferrite. So what I have here is a very simple ferrite rod. If I place this into the core of the simple transformer that we have in place in the circuit, we'll see the secondary reading improves. Whilst not perfect, it's still a good way to show students the theory of how transformers work in a practical environment. So if I change the reading here to 5 volts and then remove and insert the ferrite rod into the circuit, you can see how the secondary reading improves. Okay, so what I have now is a different transformer. This is an audio transformer with a turns ratio of 2:1. Although you can't see the construction inside this transformer, each has a winding intertwined around the other and surrounded by laminated iron plates, which provide a very good magnetic coupling between primary and secondary. So if I put this in place into our circuit with the larger coil to the left hand side, what you'll find is that the secondary output is pretty much half that of the primary on our oscilloscope. So if I change the reading to 10 volts, we can see on the primary there we've got a reading of 10 volts, whilst on the secondary we have a reading of around 5 volts. If I turn our audio transformer around to put the smaller value on the left hand side, then you'll see that the values on the oscilloscope also switch, and the primary reading becomes half that of the secondary reading. So what we have there is a very simple way to use an oscilloscope, a signal generator and the A-level Locktronics kit to deliver the A-level core practicals focused on study of electricity using this type of equipment. Thanks for listening.